Today, we're really kind of hacking the mindset of a network architect. It's one thing to know how to plug in a router, but it's another entirely to build an invisible, secure infrastructure that literally spans the globe. And that is exactly what we're tackling for you in this deep dive.
Right, which is why we're going straight to the source material today. I mean, if you truly want to master Cisco wireless networks, you really have to understand the underlying logic of the exam that certifies that mastery.
Exactly. So for those of you gearing up for it, or, even if you just want to understand the invisible data flying around your office right now, we are zeroing in on the Cisco 300120 exam.
And just to give you a quick rundown on the parameters, this is a 90-minute gauntlet.
Yeah, gauntlet is the right word.
Oh, totally.
Yeah.
You're looking at roughly 55 to 60 questions, and they go way beyond simple multiple choice. They throw like drag and drop scenarios at you, plus performance-based hands-on lab simulations. And it's available in both English and Japanese.
It's definitely a test of highly practical, applied knowledge. You really can't just memorize flashcards to pass this one, right?
No, not at all. You have to actually know how the systems interact in the real world.
Right. And our mission today isn't just to hand you an answer key. We're going to organically walk through 10 specific real-world scenarios pulled right from this exam. We'll read the full text of every question and every single option, and then forensically break down the problem-solving logic.
We're going to look at the traps the exam writers deliberately set for you.
The wrong answers, basically.
Exactly, and figure out exactly why those traps fail in practice.
So let's start right at the edge of the network. Question 1 is all about extending the office to the home. Here's the question. Which operational characteristic is unique to the Cisco Office Extend solution? And the options are: A, it prohibits the use of local home network devices. Option B, it requires the user to manually establish a VPN connection from their client OS. Option C, it operates in standalone mode and synchronizes with the corporate controller monthly. Or option D, it provides a split-access design that maintains enterprise security via hardware tunnel while allowing local network functionality.
This is a great one to start with.
My first instinct here would be, for ultimate security, the system should probably just block all of the user's local wireless devices, like shut off their home printer, keep the data locked down. But that's actually one of the major traps, isn't it?
Oh, it's a huge trap. I mean, prohibiting local devices completely defeats the purpose of the Office Extend architecture. The real brilliance of this solution is what we call a split-access design, which is option D.
Okay, so it's essentially a two-lane highway for a remote worker. One highly secure lane goes straight to the corporate office, while the other lane is strictly for local traffic.
Yeah, exactly.
Like printing a recipe at home or whatever.
That's a perfect analogy. It maintains enterprise security via a tunnel to the controller, but you still get to use your home network. So option A is out because it explicitly does not prohibit local devices.
Got it. And what about option B? Some people think the teleworker has to manually, spin up a VPN from their laptop.
Which sounds logical, right? But it's fundamentally incorrect here. The hardware itself, the access point, handles the tunnel. The user doesn't have to manually establish a VPN at all.
Oh, wow. So they just connect to Wi-Fi like normal.
Exactly. And option C is just wrong because, well, a monthly sync. You need constant real-time connectivity to route traffic and enforce policies, not a standalone mode that syncs once a month.
Okay, that makes sense. So once we have successfully connected that remote worker's laptop, we have to handle the actual traffic they generate. Like what happens when they make a voice call?
Right. Quality of service becomes critical here.
Which brings us to question 2. How does the wireless infrastructure ensure QoS for voice traffic moving from a wireless to a wired network? Option A, the controller overrides client markings based on the radio frequency band. Option B, the wired switch generates a unique session token for voice bandwidth. Option C, the access point translates the wireless WMM user priority into a DSCP value inside the CapWAP tunnel header. Or option D, the client encapsulates the traffic in a secure tunnel that inherently guarantees priority routing.
Okay, so this is about bridging the gap between the air and the wire. Out in the air, wireless devices use WMM markings.
Wireless multimedia, right? I always think of that as like a VIP pass at a concert, but the wireless VIP pass needs to be translated into a VIP pass that the wired network understands.
Yes, exactly, because wired switches don't speak WMM. So option C is the correct answer. The access point actually translates that wireless priority into a DSCP value.
A DSCP value.
Yeah, differentiated services code point. It stamps that value on the outside of the CACWAP tunnel header. That way, the wired switches see it and prioritize the latency-sensitive voice traffic.
So option A is wrong because the controller doesn't care about the radio frequency.
Right, RF has nothing to do with payload priority. A voice call on 2.4 gigahertz is just as urgent as one on 5 gigahertz.
Makes sense. And option B with the unique session tokens.
Totally fabricated. Wired switches don't generate unique tokens for voice bandwidth like that.
What about option D? A secure tunnel inherently guarantees priority. That sounds so convincing.
It does, but just putting traffic in a secure tunnel simply hides what's inside. A tunnel full of file transfers looks the same as a tunnel full of voice calls. You absolutely need QoS mapping.
Right, okay. Prioritizing voice calls is crucial. But what about other network services? How does a user find, say, a printer across a massive segmented corporate network?
Multicast DNS. This is always a fun one.
Yeah, let's look at question 3. How does a wireless LAN controller handle the discovery of services across different subnets using multicast DNS? Option A, it blocks all discovery broadcasts to prevent congestion. Option B, it acts as an MDNS gateway, caching service advertisements and smartly proxying them across VLAN boundaries. Option C, it requires all clients to authenticate with a central directory. Or option D, it dynamically merges all subnets into a single broadcast domain.
So multicast DNS, or MDNS, is usually trapped in a single broadcast domain. It is a time to live of one.
Wow, so it can't cross over to another subnet at all.
Physically impossible on its own. So if you have hundreds of subnets, how do you prevent a giant shouting match of devices looking for printers? Option B is the answer. The controller acts as a gateway.
It's like a middleman.
Exactly. It caches the advertisements and smartly proxies them across the boundaries without actually merging the networks.
Which means option D is a terrible idea, right? Merging all subnets into one massive broadcast domain.
Catastrophic. The network congestion would bring the entire infrastructure to its knees.
Good to know. And option A, blocking all broadcasts.
I mean, it stops congestion, sure, but it completely breaks the functionality. No one could find a printer.
And option C, central directory authentication.
Authentication is about security, not the underlying mechanism of MDNS shared resource discovery.
Yeah.
It just doesn't solve the routing problem.
Got it. Okay, so the network is clearly smart enough to find printers across subnets. But what happens when the disruption isn't on the network at all, but like floating in the physical environment?
You mean interference?
Yes. Question 4. How do advanced location services classify non-Wi-Fi interference sources? Option A, by analyzing specific error codes returned to network probes. Option B, by measuring the latency of client authentication requests. Option C, by aggregating end-user complaints submitted through a captive portal. Or option D, by using spectrum intelligence to continuously monitor the RF environment and analyze waveform patterns.
So many people get tripped up on this one.
I just find it so funny that, like, heating up lunch in a microwave can disrupt enterprise Wi-Fi. Do the access points basically act as environmental radar?
That's exactly what they do,
Right.
which makes option D the correct answer. They use spectrum intelligence. They continuously monitor the raw RF environment and send that data to a central platform to pinpoint the interference patterns.
Oh, so they're looking at the actual waveform.
Right, which is why option A is incorrect. A microwave oven doesn't speak Wi-Fi. It's not going to return a specific error code to a network probe, you know.
Right, I can't say error, currently heating up lasagna.
Exactly. And option B, authentication latency. I mean, that's a symptom, but it's not a method of actually classifying the interference source.
And option C is just waiting for people to complain on a portal.
Yeah, way too reactive. It's a manual process, not a system classification method.
Okay, so since the access points can pinpoint the location of a microwave, can they also pinpoint the exact location of a user and actively change their experience based on where they're standing?
Oh, absolutely. Location-aware experiences are huge now.
Which brings us to question 5. How does a location-aware captive portal dynamically customize the user experience based on physical position? Option A, the client OS natively intercepts location data to render a locally stored page. Option B, the location engine tracks the client zone and triggers API calls to push targeted web content. Option C, the controller forcefully changes broadcast frequencies to trigger a roaming event. Or option D, the access point directly injects HTML scripts into the user's active browser session.
I love this concept.
Is this like walking into a specific aisle in a grocery store and suddenly getting a digital coupon on your phone for the exact brand of cereal you're looking at?
Yes, it's hyper-localized. And the way it works is option B. The location engine tracks your physical zone and triggers API calls to push targeted web content, like customized login pages or ads, from an external server.
So option A is wrong because my phone isn't secretly storing a bunch of corporate login pages, right?
Right, it's not the native OS rendering a local page, it's a network-side push.
And option C sounds crazy, forcefully changing broadcast frequencies just to show a new page.
Oh, it would cause so many dropped connections. You'd never do that.
And option D, the AP directly injecting HTML scripts. That sounds like malware.
Yeah, that's basically a man-in-the-middle attack. The access point doesn't hijack your browser, it just redirects you.
Okay, so customizing a login page based on location is super impressive. But how does the network dynamically customize the actual security permissions and network access a user gets once they authenticate?
Now we're getting into dynamic network assignment.
Right. Question 6. How is dynamic VLAN assignment executed after client authentication? A, the client device explicitly requests its desired network segment. B, a radius authentication server checks the identity and returns authorization attributes instructing the infrastructure where to place the user. C, the controller arbitrarily cycles through subnets to balance IP addresses. Or D, the local DNS server matches host names with network segments.
This is a core identity-based concept.
I kind of think of this like a bouncer checking your ID at the front door of a club, right? And based on who you are, they hand you a specific colored wristband that dictates which VIP rooms you can enter.
That is the perfect way to look at it. The radius server is the bouncer, making option B the correct answer. The radius server checks your identity and returns authorization attributes, like VLAN IDs, telling the infrastructure exactly where to place you.
So you don't need 20 different Wi-Fi network names for different departments.
Exactly. One SID, but everyone gets put in their proper VLAN.
So option A is wrong because I can't just walk up and ask the bouncer for the all-access wristband.
Right. The client device does not get to explicitly request or choose its network segment.
And option C, arbitrarily cycling through subnets.
That would mean the CEO and a guest could randomly end up on the same subnet just for the sake of load balancing. That's a massive security vulnerability.
Wow, yeah. And option D, using the local DNS server.
DNS just matches host names to IP addresses. It's not used for authentication or authorization policies.
Okay, so the authentication server acts as the central bouncer, securely placing users. But what if that central bouncer is completely unreachable because a remote branch loses its connection to headquarters?
The classic WAN outage scenario.
Let's read question 7. What is the most appropriate scenario for implementing local web authentication on a wireless LAN controller? Option A, a global enterprise requiring database-driven portals. Option B, an environment requiring complex behavioral analytics. Option C, a highly secure isolated branch where persistent connection to a central server cannot be guaranteed. Or option D, a university campus supporting seamless roaming across independent institutions.
This one is very situational.
It sounds like a lifeboat protocol to me. Like, if it's so useful, why wouldn't we just use this local method all the time?
Because central servers are vastly more powerful for normal operations. You only use the lifeboat when the ship is sinking. So option C is correct. It's for highly secure isolated branches where you can't guarantee a WAN connection to the central server. The local controller hosts the portal itself to survive the outage.
That makes sense. So option A is wrong because a global enterprise needs a central database to manage all that complexity.
Precisely. A local controller can handle a massive database-driven portal.
And option B, complex behavioral analytics.
Again, way too much heavy lifting for a local branch controller. You need a centralized identity server for machine learning and analytics.
And option D, the university roaming.
Seamless roaming across independent universities requires central federation. Isolated local controllers can't talk to each other to share those identities.
Okay. Dealing with a total branch outage is stressful for sure, but troubleshooting intermittent, ghostly connectivity issues across the whole enterprise, that just sounds like a nightmare. How do admins actually figure out what's going wrong?
Well, they don't just rely on standard logs anymore, that's for sure.
Yeah. Question 8. How does Cisco Catalyst Center Assurance provide an advantage over traditional logs? Option A, it interacts directly with the client OS kernel to extract crash reports. Option B, it automatically blocks other traffic to reserve bandwidth for troubleshooting. Option C, it forces the client to continuously re-authenticate until stable. Or option D, it correlates historical telemetry from multiple domains to provide automated root cause analysis.
So traditional logs are tough.
It's like reading thousands of individual cash register receipts trying to figure out why a business is failing, right?
Exactly. You have all this raw data, but zero context. Assurance, on the other hand, is like an AI detective that pieces the entire timeline together for you. That's option D.
So it correlates historical telemetry from all over the network.
Yeah, controllers, switches, access points. It gives you a health score and automated root cause analysis, finding patterns that isolated logs completely miss.
Wow. So option A is incorrect because the network doesn't literally hack into your laptop's kernel.
Right. It doesn't interact directly with the client OS kernel to pull driver crash reports. It relies on network-side telemetry.
And option B, blocking other traffic.
You would never take down the rest of the network just to reserve bandwidth for troubleshooting one device.
Good point. And option C, forcing continuous reauthentication.
That wouldn't solve anything. It would just cause massive disruptions for the user.
Okay, telemetry helps find performance anomalies, but what if the anomaly is actually an active threat? Like an imposter trying to trick users into connecting to a fake network.
Rogue access points. A very serious issue.
Question 9. What action does the infrastructure take when detecting a rogue device spoofing a legitimate SSID? Option A, it performs rogue containment by transmitting deauthentication frames to disrupt the connection. Option B, it uses spanning tree protocol to physically disable the wired switch port. Option C, it transparently reroutes traffic to a honeypot server. Or option D, it downgrades encryption standards to accommodate the rogue.
The network has to protect itself here.
Is this basically the network equivalent of an immune system actively attacking a virus to protect the user's data?
That's a great way to describe it. It's an active defense. Option A is the correct answer. The infrastructure performs rogue containment by blasting out deauthentication frames. It actively disrupts the connection over the air between the user and that malicious rogue AP.
So why not option B? Why not just use spanning tree to shut off the switch port the rogue is plugged into?
Well, spanning tree protocol is for preventing network loops, not for rogue mitigation. Plus, the wireless system can't just blindly reach into the wired side and shut down ports, especially if the rogue is plugged into a neighboring business's switch.
Ah, right. What about option C, transparently rerouting to a honeypot?
Honeypots are neat for research, but in a live spoofing attack, your immediate priority is stopping the connection, not secretly observing it.
And option D, downgrading the encryption of the whole corporate network to accommodate the rogue.
If you did that, you'd be fired. It's a catastrophic security failure to weaken your own network just because a rogue device shows up.
Fair enough. All right, we've established how the network protects users from rogue APs. But finally, what protects the actual brain of the entire operation, the wireless LAN controller itself, from being attacked or overwhelmed?
Ah, the control plane.
Right. Let's hit our final question, question 10. Why is it crucial to implement control plane policing on a wireless LAN controller? Option A, to prioritize guest internet traffic over internal database queries. Option B, to frequently rotate payload encryption keys. Option C, to protect the controller's CPU from being overwhelmed by excessive management traffic or DOS attacks. Or option D, to load balance incoming client association requests across physical interfaces.
The controller is the brain.
So if I compare the controller CPU to the CEO of a major company, you can't have every single employee walking into their office at the exact same time, right? You need a gatekeeper.
Oh, I love that CEO analogy. Yes, you need an executive assistant guarding the door. And that is option C. Control plane policing protects the CPU of the controller from being overwhelmed by excessive management traffic or malicious denial of service attacks. It keeps the whole system stable.
So option A is wrong because it's not about prioritizing guest internet traffic.
Right, prioritizing data traffic is a quality of service thing, completely separate from protecting the CPU.
What about option B, rotating payload encryption keys?
That's a security protocol function, like WPA3. It has nothing to do with control plane policing.
And option D, load balancing client requests.
That's about link aggregation, managing bandwidth across physical ports. It doesn't protect the CPU itself from a traffic storm. Stepping back, mastering the logic behind these questions, understanding exactly why those trap answers fail is really the absolute key to passing the Cisco 30012 exam. You're shifting from just memorizing facts to genuinely thinking like an architect.
Absolutely. And here is a final thought for you to mull over as you prepare. Next time you walk through a busy corporate office, just think about the invisible complexity happening in the air all around you. Your phone isn't just connecting to Wi-Fi. It is actively navigating a silent, invisible battlefield of spectrum intelligence, dynamic identity checks, prioritizing encrypted voice packets, and firing off active rogue containment, all happening reliably at the exact speed of light. Let that sink in for your exam prep.